No, this is an easier chapter, isn't it? Huh? Yeah. Okay, we're going to do a review. Chapter 13, chemical equilibrium, and I've highlighted the ones in the review document that I want to be sure and get to. Let's see here. I can get those two on the same without moving. Number one. Which of the following statements about the equilibrium is false? So they're referring to this equilibrium where you have hydrogen gas plus diatomic iodine yields to, oops, hi, yes. All right, so we need to look, they're all unique answers, so we need to look at each one of them at least until we find the correct answer. If the system is heated, the right side is favored. Let's see, is there any more information? No, that's it. If the system is, how do you know? How do you know which side is favored if you change the temperature? We don't, because the enthalpy is not given for this reaction. So I don't see how we can take A as a correct answer. Okay, so I wouldn't even say true or false, I'd just say unknown. Of course, it won't answer the question. Which one is false? That's the key. So, all right, if we need to make an assumption, most synthesis reactions are exothermic. In other words, when you go from elements to a compound, it's usually more stable, which means that it's probably this, right? But we don't know. All right. B, this is a heterogeneous equilibrium. Heterogeneous, that means it has two or more different phases. That's true. It has gas and solid. If the pressure on the system is increased by changing the volume, the left side is favored. Okay, so when we're going to change the pressure, the only thing we have to be concerned with is gases. We've got a gas here, we've got 1 mole of gas here, we've got 2 moles of gas here. So when you increase the pressure, the response of the system is to try to reduce that pressure. And it does that by changing the number of moles. If we decrease the moles from 2 to 1, we'll decrease the pressure. So once the stress is applied, then the reaction should shift to the left to give us fewer moles of gas. D, adding H2 gas increases the equilibrium constant. How do we change the equilibrium constant? Temperature. And adding or removing reactants and products won't change the equilibrium constant. It'll change the equilibrium position, but not the constant. So this one is definitely false. And the last one, removing HI as it forces the equilibrium to the right. Yes. If we can remove this somehow, then it will force the equilibrium to the right. So this one is definitely false. And this one is speculating to be true. All right. Number 2. Which of the following is true for a system whose equilibrium constant is relatively small? If the equilibrium constant is much, much less than 1, that means that, and it's equal to, if we have A plus B, let's see, that's B, this is A, and then C plus D. And we have the equilibrium constant written this way. And if this is very, very small, that means we have very little product and mostly reactant still. That's well, it's just math. So which one of these is true? Which of the following is true for the system? It will take a short time to reach equilibrium. What does time have to do with equilibrium? Nothing. Equilibrium is just when it gets there. It may take a few milliseconds. It may take a couple of hours. It might take a million years. Right? Equilibrium says nothing about time. That's kinetics. So A and B both refer to time, have nothing to do with this one. With the concept of equilibrium. They're both false. The equilibrium lies to the left. Well, yeah, we just said that. The denominator needs to be big, numerator needs to be small. So C is true. Now, actually, we found our answer. Can't be two of these because we've eliminated the first two, and C and D are mutually exclusive. So it has to be C. Number 3, let's see if we can get all that on there. For this equilibrium, right? CO2 plus H2, CO2 gas plus hydrogen gas is in equilibrium with carbon monoxide gas and water. All gases. And the delta H for this reaction is endothermic. All right. K equals 1.6. So K equals 1.6, and that's equal to, let's see, are we given these in placed in the meter? We're given moles per liter. All right, so we're gonna express these as molarity. They're all gases, so we will include them in our expression. Because gases can change composition, concentration. And they're each coefficients of 1. All right, we're given that so far. And this is at 1260 K. Better put an EQ down here to distinguish temperature from constant. We're placed 0.15 mole each of CO2, each one of them, 0.15 mole in 1 liter. So it's 0.15 molar. Actually, that's not the equilibrium expression. What we've got here is Q equals 1.5, let's see, 0.15, excuse me, per mole, 0.15. I use a parentheses rather than a square bracket to denote that this is not an equilibrium. Okay. Thermally insulated vessel, then as the system came to equilibrium, the temperature would decrease and the mass. Okay. Okay. So as this system comes to equilibrium, what we need to know is which direction is it going to move, right? So if we do Well, Q is equal to 1, isn't it? Right? This the same on top and bottom. Q is equal to 1. So if Q is equal to 1, what we're saying is the situation is that there's too little product and too much reactant. Correct? To be 1, we'd have to decrease this to make this shift to 1. So decrease the product. So that means it's going to shift to the right, correct? Yeah. So we're saying that with this Q and this K, we're shifting to the right under these circumstances. What else does that mean? Well, if this is an endothermic reaction, it's going to absorb heat from its surroundings. That means the temperature decreases, at least temporarily. Okay, so the temperature decreases. That means it's either A or B. And the mass of CO2 would what? Increase or decrease? Decrease. CO2 mass decreases because we're shifting to the right for that balanced equation. So that means what? B is the answer. Okay. Now, number 3. Let's see. Who's next? 4. Okay. 4. Addition of chemical B to an equilibrium mixture of the above will what? Oh, okay. So I need to put this one, and this is going to be used for 4, 5, and 6. So let's do that first. 2A gas is in equilibrium with 2B gas plus C gas. And the delta H, no, the K is given. 1.6 times 10 to the 4th. And the expression then, you might as well do the expression while we're here. B squared times C to the first power divided by A squared. There we go. Okay, now we can talk about these individual situations. 4. Addition of chemical B to an equilibrium mixture of the above. If we add B, the equilibrium is going to shift to the left, which will consume the B and C and give us A, cause A to increase. Yeah, that's the only one that works out of that group. About 5. At a higher temperature, K equals 1.8 times 10 to the minus 5. So temperature increase, and it doesn't tell us what the temperature is. Then K equals 1.8 times 10 to the minus 5. Placing the equilibrium mixture in an ice bath, thus lowering the temperature, will what? Well, at a higher temperature, if we increase the temperature, the K gets smaller. And then if we decrease the temperature, the K should get bigger. Correct? I mean, that's the logic. If K gets larger, that means product should be favored over reactants. So A should decrease, B would increase. Yeah, B would increase. And that would be B. Does that make sense? Or do I go over it again? See, all I'm saying is that we know that increasing the temperature decreases the K. So decreasing the temperature, which is what they tell us to do, the ice bath, should take us back here plus lower temperature. Lower temperature would be higher K. Okay, raising the temperature by lowering the volume of the container, raising the pressure by lowering the volume. All right, these are all gases. You've got 2 moles here and 3 moles here. So if we increase the pressure, we're going to go from 3 to 2. So that would be A would increase. Okay. All right. Let's see. Okay, we've got another equation referencing to this number, problem number. So let's get the equation up there. Number 8 is based on let's see. That would be hexahydro cobalt 2 plus. Okay. And then we add 4 chlorides. That's in equilibrium. Oh, this is pink. That's a complex ion. Two minus, yeah, plus 6 waters. Okay, this is blue. All right, now what's the question? Which statement below describes the change that the system will undergo if hydrochloric acid is added? So we're going to add that, which means what? We're actually adding hydrogen ions plus chloride ions. There are no hydrogen ions in here to affect this equilibrium, but there are chlorides. So we're adding chloride ions right here. So we should eventually turn this thing blue. It should become, let's see, does it give us a beginning situation? And if you don't want it. Okay, it doesn't say. It should become more blue. Yeah. Okay, so it's going to become, they say more blue because maybe it's blue already. Okay. It'll either turn blue from pink or it become more blue. And then B should become more pink. Nope, won't go that direction. We're headed this way. Equilibrium shift to the right. Yeah. So actually it's A and C, which means E is correct. 2 of the above. All right, got another one. Number 9. Based upon 2H2 gas plus X2 gas is in equilibrium with 2H2X gas plus energy. Right, so this is an exothermic reaction from left to right. All right, what are our choices? Addition of X2 to a system described by the above equilibrium will what? Cause H2 to decrease? Yeah, it will. Because when you add this, it's going to shift to the right and use up some of that. Cause X2 to decrease? No, it won't cause X2 to decrease from its equilibrium position because we added some. So it'll decrease from the added amount, but based on its equilibrium position, it'll still be higher. It'll only decrease as far as it takes to get to equilibrium, but the X2 concentration will be higher than it started at equilibrium. It won't cause this one to decrease because it's headed that direction. Right, so A is the only possibility. A is our answer. right? Let's see. I'm not going to need that again, am I? No. We're moving on. Number 11. Which of the following statements is true? Let's see. A, B, C, D, none of the above. Okay, so we have to actually, all we have to do is find one that's true, and then E can't be possible. All right, so the first one, when two opposing processes are proceeding at identical rates, the system is at equilibrium. That's the definition of equilibrium. Opposing rates are equal. Catalysts are an effective means of changing the position of an equilibrium. That is false. Catalysts don't change equilibrium, they change kinetics. They change the rate of reaction. All right, how about C? Well, E can't be true anymore because we got a true one here. In fact, that's our answer. So C and D must be false. The concentration of the products equals that of the reactants and is constant at equilibrium. No, concentration can be anything that the reaction desires. It's the rate that matters. An endothermic reaction shifts toward reactants when heat is added to the reaction. An endothermic reaction. So we have reactants, yields, products, plus, nope, the other way. Delta H on this side, endothermic. So if we increase the temperature, we add heat, we're moving toward products. Right, so that D is false also. It says you move this way, but you don't. When you increase that, you go to the right. Okay. So A is our answer. Number 12. Let's see. Consider this reaction. Right? They're not even coefficients here. All right. A plus B yields C plus D, and they're all gases, aren't they? Yeah. Unless we have to assume that the coefficients are all one. One. We got equal moles of gas on both sides. Upon adding gas A, the value of K, what? Well, if you add something to a reaction at equilibrium, it doesn't change the K. Right? It only changes the position. So the value of K increases? No. Decreases? No. Does not change because A does not figure into the product to the reactant ratio. Now, that's not true. A is there. They're all gases, so A has to be part of the expression. Right? A will be the concentration of A, excuse me, C, D over A, B. So if this doesn't change, right? No matter what we do. But does it change because A does not figure in? No, A's there. It does not change D as long as the temperature is constant. So D is the only one that makes sense here. And it doesn't depend on endothermic or exothermic. Because adding A does nothing to the reaction. Does nothing to the equilibrium constant. Equilibrium only shifts for endothermic and exothermic depending on temperature. All right, let's look at 17. A Ammonia is prepared industrially by this reaction. It looks familiar. N2 gas plus 3H2 gas is in equilibrium with 2 ammonia gas. And the delta H under standard conditions, that's what that 0 means. Minus 92.2 kilojoules at 25 degrees, which that's what this means. And the K equals 4 times 10 to the 8th at 25. 4.0 times 10 to the 8th at 25 degrees C. When the temperature of the reaction is increased to 500 degrees, which of the following is true? If we increase, this is an exothermic reaction, right? So that becomes a product. That heat becomes a product. That's what the negative sign means. So that's the way I look at it. If we're going to increase the temperature from here to 500, which of the following is true? Well, let's see. Let's see. K for the reaction will be larger at 500 than at 25. No, the K will decrease as we increase the temperature because we're driving the reaction back this way. That makes this smaller and this larger. So the K will decrease. So it won't be larger, it'll decrease. At equilibrium, more ammonia is present at 500 than at 25. No, if the K decreases, then less ammonia is present at 500. Right, so concentration of ammonia decreases. All else being equal. Right? Product formation at equilibrium is not favored as the temperature is raised. That is true. Because as you increase the temperature, you're adding this factor to the product side, and that drives the reaction backwards. Actually, it changes the equilibrium constant. So we found our true answer. The reaction of N2 plus with H2 to form ammonia is endothermic. No, I don't think so. The negative sign says it's exothermic. So none of the above are true. That's wrong. C is the only true one in that group, based upon the conditions we were given. All right, number 20. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. Okay, so we have 2 mercury 2 oxide solid, and it decomposes to mercury solid plus oxygen gas, correct? Yep. And the delta H is plus 43.4. Oh, they're using calories. All right. Kilocalories. All right. How would we increase the mass of reactant here? Well, one way is to either add more oxygen or add more mercury. That would do it. Yeah. So removing some mercury would not do it. Right? A is false. Reducing the volume of the bulb. Well, let's see, what would that do? If you reduce the volume of the bulb, You increase the pressure, and there's only one gas in here. So in order to relieve the pressure stress, you'd have less oxygen once you reach equilibrium again. You just change the pressure by decreasing the volume, shift it this way. That's true. Add more mercury. Adding more mercury. Look at the equilibrium expression for this thing. What is it? That's it. Because it's a gas. And solids don't change their concentration. So adding more mercury won't move the equilibrium. Did I say add product? I did say add product, but I wasn't specific. In the beginning, add product, but this is the only product that will move the equilibrium. Solids won't move the equilibrium. Let me correct myself. Increasing the temperature. Well, if this is endothermic, then the delta H is on this side. And if we increase the temperature, it'll drive the reaction to the right. That's the wrong way. We don't want to go that way. And if we remove some oxygen, that'll drive it to the right also. Right? So B, reducing the volume of the bulb, is the only thing of our choices. That's the only one of our choices that will produce more mercury 2 oxide. Right, 2021. At 500 K, 1 mole of gaseous, whatever that molecule is, ONCl, is placed in a 1 liter container. 1 mole in 1 liter is 1 molar. At equilibrium, it is 5.3% dissociated according to the equation shown below. Determine the equilibrium constant. Okay, I smell ice table. So we have 2ONCl is in equilibrium with 2NO plus Cl2. And these are all gases. Does it say that? 1 mole of gases. All right. Well, we know this is gas at standard temperature. We know this one is gas. We're told this one is gas. So if they're not all gases, then one of them might be eliminated. So we have to assume that they're all gases. All right. What's the initial concentration? 1 mole of this per liter is placed in the container. So it's 1 molar. And there's none of this. The initial concentrations there are 0 for our products. At equilibrium, 5.3% of the reactant is dissociated. So this reaction goes that way by 5.3%. That is, we're changing it by 0.053, right? The decimal equivalent of 5.3% times 1 molar. That's what we're losing. It's preceded by that much. And so we have 1 minus 0.053. I'm not going to trust my mind today to do this in my head. Is 0.947 molar at equilibrium. Okay. And actually, this is 0.053 molar. Okay. So if we lose this much to that side, since this is 2 to 2 or 1 to 1, we're actually adding 0.5053 molar here. and half of that over here. So what's half 0.5053? Oops. 3 is 265. I'm going to keep that extra decimal for now. Okay, so what do we have here? Well, we have 0.053 molar. And this one we have 0.0265 molar. Now we can calculate the equilibrium constant, correct? What we need is the concentration of NO squared, chlorine to the first power, and ONCl squared. So we just plug in our numbers. That's the hard part. That's the thinking part. This is all the thinking part. It's 0.265. It's divided by 0.947 squared. So let's see, 0.053, and we'll square it times 265, and then divide by 0.947, but I have to square it first. So I get 8.3 times 10 to the minus 5. That's A. Okay. A. One nice thing about the ice table is it keeps your mind focused and doesn't stray. Keeps your mind on the problem. Yeah, okay. Let's take all right, we got a new reaction coming up. I can erase this one. I guess one of the key things is recognizing when you need an ice table. Definitely, if they're asking for you to calculate the K, you're going to need an ice table. No doubt about that one. Or if you need to calculate a concentration of one of the reactants or products, you'll need an ice table. Okay, for this reaction, calcium carbonate, solid. And so it's not going to be part of the equation. Yields calcium oxide, solid, plus oxygen gas. Correct? Oh, CO2, sorry. CO2, there we go. Yeah, I just destroyed carbon. So if a 31.3 gram sample of this material, right, is put into a 10-liter container and heated to 800 degrees. So we've got a volume of 10 liters. Let me just put everything over here that we know. And our temperature is going to be 800 degrees C. What percent of calcium carbonate will react to reach equilibrium? All right. We're given the K. K is 1.6. Kp is 1.6 at 800. So let's see, where do I put that? Kp. No, that's not a good place for it. Let's put it over here. .16, and that's equal to the partial pressure of CO2, right? Because it's the only gas in here. These solids don't count. That's the partial pressure at equilibrium. Okay. So guess what? This is the only term. And we have to assume that the pressure is in atmospheres. So that means the partial pressure of the gas is equal to 1.16 atmospheres. That's one of the tricks to solving this problem. Since this is Kp, that's partial pressure, and there's only one factor, so it's got to be equal to that value, 1.16 atmospheres. Now we can find out how many moles are produced and the concentration of CO2 under these conditions, right? Okay, so, right, use this one. N equals PV over RT. So pressure is 1.16 atmospheres, volume is 10 liters. Temperature, R is 0.08206 liter atmospheres per mole K. And this one has to be 1073. Okay. There we go. So we can find out how many moles of CO2 were produced. Calculator. So this one is 11.6, right? Because 1.16 times 10. And 0.08206 divide and 1073. So this is 0.132 moles of CO2 are produced. Okay? It's 1 to 1 to 1. So moles of CO2 is actually moles of calcium carbonate consumed. Right? So how many moles is this? Well, see, how many grams is that? Because they want us to answer it in terms of percent. What percent of CO2 will react to reach equilibrium? What percent of that is this in mass? So what we need is calcium carbonate molar mass. All right, calcium is what? It's about 40, I think. 40.08. 40.08. Should I write that in here? 40.40. Right. 40.08 for calcium, and carbon is 12.01, and 3 times 16 is 48 for oxygen. Okay, so add those together. And is 100.09. Okay, that's times 0.132, which is 13.2 grams of calcium carbonate were used. So what percent will react? All right. So the percent that reacted was 13.2 divided by 31.3 times 100. And I get 42%, 0.1% reacted. Okay. There are a lot of steps in that problem. I think the key is recognizing this is pressure. When it says Kp, that's K pressure. So that's equal to 1.16. And the only term in there that contributes to that value is the pressure of carbon dioxide. So at equilibrium, you got 1.16 atmospheres. That's where we get all this information needed to solve this problem. And then it's just step, step, step. Okay? Those type of problems may take some practice. And remembering your gas laws. We didn't learn those just so that we could forget them last semester. 24. How we doing on time? All right. Nitrogen gas reacts with hydrogen gas to form ammonia, right? That's the Haber process. At 200 degrees C in a closed container, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen. At equilibrium, the total pressure is 2.2 atmospheres. Calculate the partial pressure of hydrogen gas at equilibrium. All right. Let's see. They don't even give us a K, do they? Was it given to us up here? No. I don't see a K in there. So we must be able to solve this without the K. So let's write the equation. Nitrogen gas plus hydrogen gas is in equilibrium with ammonia gas. Yeah, let's see. Back. All right, so that's what we're working with. At 200 degrees in a closed container, we have 1 atmosphere of nitrogen gas is mixed with 2 atmospheres. We have 1 atmosphere here and 2 atmospheres there, and obviously 0 there. This is an initial condition. Okay. At equilibrium, the total pressure is 2.2 atmospheres. So at equilibrium, the pressure of N2 plus the pressure of H2 plus the pressure of ammonia equals 2.2 atmospheres. We add those 3 together. That's our total pressure. And they want to know the partial pressure of hydrogen gas. Well, how are they related? You've got this represents 1 mole. This represents 3 moles. And this represents 2 moles. So the ratio is 1 to 3 to 2. Right? So what's that total? 1 plus 3 is 4, 5, 6. So 1/6 of that pressure is nitrogen. 3/6 is hydrogen, and 2/6 is ammonia. So 3/6 or 1/2 of that, 1.1 atmospheres, should be hydrogen. Oops, I did something wrong, didn't I? 0.8. What did I do wrong? Let's see. The ratios are right. I made a mistake somewhere. How did they change? Well, we're going to lose X here, right? We're going to lose 1 to 3, 3X here, and we're going to end up with 2X there. So maybe that's a better approach. Right? This is still true. Right? That's still true. But the K expression then would be, let's see, 1 minus X, 2 minus 3X, and 2X. And these 3 together equals 2.2X. Let's try that one. So this is 1 plus 2 is 3. Is 3. Let me put it out here. 1 minus X plus 2 minus 3X plus 2X equals 2.2. Okay, so these are just numbers, so that's 3. And then the x's. A minus x and a minus 3x is minus 4x, and a plus 2x is a minus 2x equals 2.2. So let's bring this one over here. 3 minus 2.2 equals plus 2x. Everybody see what I did there? Okay. And 3 minus 2.2 is what? Let's see, 0.8. Is that right? Yeah, 0.8 plus 2.2 is 3. It's equal to 2x. So x is equal to 0.4. And they want to know hydrogen. So this one. This one is 2 minus 3x. So it's 2 minus 3 times 0.4. So this is 1.2, right? 2 minus 1.2 is 0.8. Okay. That's the solution. We still had to use the ice table. Let's see, this one would be what? If this is 0.8, 0.8. And this one is 1 minus x, which is 0.6. 0.6. And this is 2x, which was the 0.8. So 0.6, 1.4, 2.2. Okay, they all add up. I was just checking the math. Dalton's law of partial pressure says this one plus this one plus this one has to equal that one. We can calculate K now that we know these values, but that wasn't the question. The question was, what's the concentration of hydrogen gas? All right. Okay. We got the same equation for 25. And the question in this case is, what is the equilibrium constant? Let's leave that up there and just change this part right here. We'll set up another ice table. I'm sure we're going to need it. We're going to calculate K. We've got to have the ice table. All right, what are we given? 2 moles of nitrogen, 4 moles of hydrogen in a 1 liter container. It's backwards. All right, they're going backwards. Sorry. No. They put hydrogen first. All right, I'm going to leave it that way. We're just going to put the correct values in here. 2 moles of nitrogen in 1 liter is 2 molar. Right. And 4 moles of hydrogen in 1 liter is 4 molar. Right? Everything in equilibrium is based on concentration. Remember that. And there's no ammonia yet. All right. The equilibrium concentration of ammonia equals 0.55 mole per liter. 0.55 molar at what? 700 degrees, was it? The value of K at 700 degrees is what? Well, let's see. If we came to 0.55, that means we had to add 0.55 molar because we had nothing to start with. That means that half of that value is from here. 0.55. What's half of 0.55? 0.275. And 3 times that is what was lost from hydrogen. Or 0.825 molar. Okay, so let's subtract that one from 2 and this one from 4. This will be 3.175 molar, and this one would be, let's see. Yeah, do that one again. 1.725. Okay, now that we have our equilibrium concentrations, it's easy to calculate K. Right, gas, gas, gas. That means, right, ammonia gas squared over nitrogen gas to the first power times hydrogen gas cubed. And we just plug in our numbers. Right, so ammonia is going to be over here is 0.55 squared. And then nitrogen is going to be 1.725 to the first power. And hydrogen is 3.175 third. So now we just crunch some numbers. Let's see. Let's keep that one. I get 5.5 times 10 to the minus. That would be C. Did I lose anybody? See how this gave us, this is where our initial concentrations, but this told us how things changed because we knew this was 0 to start with. That gave us that value. Then all we had to do is the mole ratio to give us these values. That had to come from somewhere, and it came from here, this change. So we just subtract that and that, and that gives us those values, and the rest is
hydrogen, like 0.825.
oh,
I kind of got the.
this is the ratio 1 to 3. If we lose this much, right, this ratio is 1 to 2. Right, so if we lose that much, twice that is what we end up with over here. And then if we lose this much from one coefficient here, then the 3 coefficient here means you had to lose 3 times as much of hydrogen. Yep. Okay. Can I erase? No. Okay. Oh, there's Kathy. Okay. All right. Let's see what's coming up. 26. Different equations. All right. We're going to use Hess's law, it looks like to me. All right, given the equilibrium constants for the following reactions. What's the K for the system? All right, so we have 4Cu solid. Plus oxygen gas is in equilibrium with 2Cu2O solid. And this is given the value of K1. Then we have 2CuO solid. Oops, yields. So this one's over here. Cu, oops. 2O solid plus 1/2 O2 gas. And this is K2. And the target is up here. 2Cu solid. Yeah, plus O2 gas is in equilibrium with CuO solid. And the question here is, what's the K expression for that? All right. So what we have to do is rearrange these two so that they'll give us this one. We've got copper's correct on this side. Like copper on this side, copper on this side, oxygen on that side. But there's too much of it. Right? There's too much of it. So what we have to do is say, we need to take 1/2 of it. Correct? What does that do to the K? The K is raised to that same power. It changes the K. So now the K is to the 1/2 power. And that gives us a 2 here, a 1/2 here, and a 1 there. Right, we used that up, so there we go. All right. How about this one? Let's see, I forgot to close this. There we go. All right, for this one, we need copper 2 oxide on this side. Plus, we need 1/2 of it. So we have to invert and raise it to a power. All right, so we need to put this one, we need to put Cu2O. I'm going to do it one step at a time. So I'm going to do this one on this side. Yeah. Oops. Don't forget the oxygen. 1/2. Yeah, 1/2 O2. 1/2 O2. Did I write those correctly? Half of this one, that means 2 here. 1/2 O2. Yeah, okay. And then this one is CuO, C2O, 1/2 O2. Okay. Just a minute. Okay, we do need to invert them because we need CuO on that side. All right, so these come over here. This one comes over here. Okay, so inverting them now makes the K what? Inverted. Because we switched places with reactants and products, so that just means we have to invert the K. Okay, so now we're working with this equation and this equation, but well, that should work. That should work. Why? Because Cu2O is not anywhere up here. But it's on this side here, on this side here, that means it cancels. Okay. And now we have 1/2 oxygen here and 1/2 oxygen there with a copper here. So we have 2 coppers. Let's see, we're going to combine these. We have 2 coppers solid, because there's, let's see, there's 1. And then the oxygens make 1 oxygen gas. And then we have what's left over is here, 2 CuO. That's why I put these asterisks so I don't get confused with this one. We're only using that one and that one. So we combined these two to make one oxygen. We brought this 2 copper down. That's everything on this side. Then on this side, all we had was this one, 2 CuO, solid. Okay, what does that do to the K's? When you combine equations, you multiply the K's together. So we would have K1 to the 1/2 times 1 over K2. Let's see, what do we have? What are our choices? Okay. Combine these two. This is in the numerator, that's in the denominator. So our new K is equal to this K1 to the 1/2 divided by K2. That would be E. Okay, did I lose anybody? Questions? Yep.
On the first asterisk one, how come there's not a CU2?
Oh,
Should be, at the bottom, when you add them together, it should be 3 CU2, right?
well, we have 2. Since we multiply by half, we've got 2 coppers. We've got a half an oxygen and 1 CU2O. Then we add that equation with this one, which is made from this one, which we had to flip it. So these 2 come on this side, that one goes on that side. This CU2O is on the left-hand side of the arrows, and that one's on the right-hand side. So they cancel. Maybe I need to do something like, so you see one side from the other. So that cancels these 2. And that leaves on this side 2 coppers and a half, a whole oxygen. And then on this side, we're not looking at this one anymore. We're looking at this one. The only thing left on this side is just 2 coppers because that canceled out. 2 copper oxide. Copper 2 oxide.
I was adding those 2 together.
These 2?
No.
These 2?
Yes.
Right. That one's already gone. It's history. And it's a good thing too, because there's no copper 1 oxide in the final equation. That would be a clue. If you end up with copper 1 oxide down here and you look at where you were headed, right, you took a wrong turn somewhere. That Bugs Bunny took a wrong turn at Albuquerque. Okay, still, okay, I'll wait. Right. Next, 28. Exactly 1 mole of N2O4 is placed in an empty 1 liter container and is allowed to react to produce 2 NO2s. If at equilibrium, N2O4 is 37% dissociated, what's the value of the equilibrium constant for the reaction under these conditions? This was kind of like one we've done before. N2O4 gas is in equilibrium with 2 NO2. I believe that's correct. Yes. And we start off with 1 mole in 1 liter. So it's 1 molar here, initially. This is 0. So we know which way the reaction is going to go. It's got to go that way. And the conditions actually tell us. if at equilibrium, N2O4 is 37% dissociated. If it's 37% dissociated, it's lost 37% of this value. Right? So it loses 0.37 molar. 37% of 1 is 0.37. So that means we have 0.63 molar left. Well, the ratio is 1 to 2. So twice this amount ends up over here, which would be 0.74 molar. Okay, those are the equilibrium concentrations. And we want to calculate the K. Yeah. So the K equals NO2 in molar concentration squared divided by N2O4 in molar concentration. So we have 0.74 squared divided by 0.63 in the first part. And that should give us our K. And I get, it's in standard notation. So let me see, I'm going to 0.87. That would be E. Okay. Right. Next, 29. Do some scrolling here. For this reaction, we looked at this one a little earlier. We know that's a gas. It may not be important, but this is a solid. And that gives us 2HI. I think that was a gas also. For which K equals 44.8. Very large number. It goes essentially to completion at a high temperature. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the concentration of hydrogen. All right, so we got initial change, equilibrium. And we're also told that the concentration of product is 0.5 at equilibrium, 0.5 molar at equilibrium. That means it started out at 0. So we had to get this much added. All right, so how much did we lose from this side? Well, we lost half of it here, 0.25 and 0.25. All right. Equimolar mixture. So we've got the same molar concentration here as here. All right. Determine the equilibrium concentration of hydrogen. All right. We have to use an unknown here because we don't know what it is. We do know that they're both the same. And we do know how much we lost from each side because this one tells us that twice as much was gained as was lost. So we lost this much to give us that much. So that means X minus 0.25 and X minus 0.25. Okay. Now let's stop for just a second. If we plug those into the expression, actually, are they saying that these both are gases? Because we had a problem earlier, didn't we? I think it was before you guys got here, which says that's a solid. This is a solid. Go back to 29. At a high temperature. All right, if it's at a high temperature, my guess is that they're all gases. And if that's the case, then the K expression for this one is HI squared divided by H2 to the first power and I2. Like that. And that's equal to 44.8. All right, so if we plug in these values, then we have 44.8 equals 0.5 squared divided by x minus 0.25 also squared. Why can I say that? Because the same number here is here, this one times this one is squared. All right. Now, this number is so huge that there's not going to be much x left. Does that make sense? Right. Almost all the x is going to be used up because this value is so large. So I'm thinking, well, actually, that doesn't give us any advantage. Right, because we don't have an x. If we say x is very small, and let it go to let this be approximately the same, then we don't have any x's left, so we can't solve the problem. So we've got to go with quadratics. 0.5 enter and squared is 0.25. Right, in the numerator. And expand the polynomial, right? Remember how to do that? X squared minus 0.25 times 0.25 is 0.0625 plus 0.0625. That's this part. That's squared, and then this one times that one plus this one times that one. And so it's going to be minus 0.25 x plus, well, minus, simple, minus 0.25 x. Right. So we finally have, let's put it over here. 44.8 equals 0.25 over x squared minus 0.5x plus 0.0625. Okay, we got to get all the x's on one side, so we have to bring this whole thing over here times 44.8. So that's 44.8 x squared, okay? Minus half, minus half of that, 0.5 times 44.8 is 22.4x plus 0.0625 times 44.8. 2.8. Okay, and that's equal to 0.25. Now, if we're going to solve a quadratic, remember, everything has to be on this side and zeros on the other side. So we'll say subtract this from this side. We got 44.8x squared minus 22.4x plus what's that? 2.55, right? Equals 0. Now, what's the quadratic equation? I got it on the back of my calculator. All right, so x is going to be, and x doesn't tell us, we have to say x minus 0.25 once we find out what x is. X is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. So this is A, this is B, and this is C. Remember? Okay. Here we go. Minus B, minus a minus 22.4. 22.4 plus or minus square root of B squared minus 22.4 squared minus 4 times A 44.8. Yeah. Squared. And then C, 2.55. All over 2A. There we go. So the first, let's reduce this part of the equation since it's plus and minus. We need a value for this one. So 22.4 and a square, which is 50.176. And then let's do this one. Oops. About to make a big boo-boo here. That's squared. Just 4ac. Okay, and then subtract that from that one. So underneath this square root, I'm going to go ahead and take square root of it. So now we have 22.4 plus or minus, and this all reduces to 6.69. Right? Divided by 2 times 44.8, which is 89.6. So we have two possibilities. Right? If we add 6.69 to 22.4, and then divide by 89.6, we get 0.325, or if we take 22.4 and subtract 6.69, or did I do that one first? No, I didn't. I should get 0.175. 0.175. I'm going to do those again just to be safe. 22.4 plus 6.69 divided by 89.6. Yeah, 325. And then 22.4 minus 6.69 divided by 89.6. Yeah, 0.175. Okay, so we have two choices here. Which one makes sense? Well, 0.175 minus 0.25 is a negative number, right? If we put 0.175 in here, then this becomes a negative number, right? So that can't be it. It has to be 0.325. So if x is 0.325, 0.325 minus 0.25 that says 0.075 molar is H2. Or 7.5 times 10 to the minus 2. That was a lot of work just to get that answer. I'll admit, it was a lot of work. Mainly because of the quadratic. We were stuck using the quadratic. There was no way around it because X was only in one place. We can't say that X is. Well, the other possibility is, I don't know. What if we tried it this way? If we said X minus 0.25 times X minus 0.25 and just eliminated one of the X's, then we'd be left with only one X. Then we can solve it for X and see how close we got. But it's already 9:30. 9:30. We got till 10:30. Let's see, how many more do we have to go? 29? Let's see. I got highlighted. Yeah, we got a few more to go. So I better not waste time doing it. But that's a possibility, right? If you separate them out like this, and then just say one of them is too small to be considered. Then you would have 0.25 times X minus 0.25, and then you don't have a squared X. You don't have a polynomial to solve with your quadratic. This way we get the exact answer and there's no question about it. How's your son?
He's got the flu. So
Yeah. Have you had it this season?
I haven't, no, but I had the shot.
Oh, good.
Remember, he got it, I know my oldest son got it, but it's just been rough.
Yeah. How old is he?
He's 8.
Okay, so he goes to school and picks it up and brings it home, right?
Yeah. Either that or I brought it home, one of the two.
Oh, that's right. Yeah, you're just as exposed as he is.
Yeah.
Okay, let's go to 30. All right. Consider the following equation. 2HF gas is in equilibrium with H2 gas and F2 gas. And then the K is equal to 1 times 10 to the minus 2. Okay. Given 1 mole of HF gas, 0.362 moles of H2, 0.75 mole are all mixed in a 5-liter flask. What's the reaction quotient? Oh, okay. So the Q is going to be the same as the K, only with non-equilibrium values. Let's see. If I put it there, it's gonna overlap. Let's put the values in here first. We only need to know the initial to calculate Q. So we got 1 mole of HF in 5 liters. So it's 1 divided by 5, which is what? 0.2 molar. And H2 is 0.362. 2 in 5 liters. I need my calculator for that one. 0.362 enter 5 dollars. 7.424. 7.24 times 10 to the minus 2. And then, let's see, come down here for F2. 0.75. 0.75 moles divided by 5 liters is 1.50 times 10 to the minus 1. Okay. So we got our molar concentrations but not at equilibrium. And we can calculate the Q, we just need the expression. They're all gases, so that means H2 up here, F2, and then in the denominator, HF squared. So if we put in the H2, 7.24 times 10 to the minus 2. And then F2, 10 to the minus 1, divided by 0.2 squared. Let's see. Yeah, I got those still in my calculator, these two, so I just have to hit the times button. And then 0.2 squared and divide that. So I'll get 0.272. B. Right? B is our answer. That was simple. The hard part was calculating concentrations. Let's see, 32 coming up. In a second. Everybody a chance to notate. All right. Okay. Let's see, 32. Carbon disulfide and chlorine react with the following reaction. Let's see, 2.14 moles carbon dioxide, 5.81 placed in 2 liter. Found to contain, how many moles of Cl2 are present at equilibrium? Okay. We're not given no, we're not given a K. This is kind of like that earlier problem. Let's see if we can figure this one out. Carbon disulfide plus chlorine gas. This is shaping up to be a really noxious experiment. S2Cl2. It's also a gas. And then carbon tetrachloride. Yes. Okay. 2.14 moles of CS2 in 2 liters. The initial concentration here is 2.14 moles per 2 liters. Equals what? I have to divide by 2. 1.07 molar. Right? How about chlorine? Chlorine is 5.85 moles. 5.85 moles in 2 liters, which is equal to half of that. Let's see. 2 minus 8, rounded off, molar. Yeah. Okay. Allowed to come to equilibrium. There's nothing here, nothing here. So we have a change and then we have an equilibrium. Right? 0.620 moles of this one. 0.620 moles, and we're still in 2 liters, which is 0.310 molar. That means we had to add that much, 0.310 molar. How much of this did we add that? We may not need it, but I'm going to do it anyway. Same amount. Right? So at equilibrium, we have this amount. Okay. If we added this much from the reactant side, the ratio is 1 to 1 here. So this one had to be minus 0.310 molar, right? Due to the stoichiometry. And then this one would have to lose 3 times as much. So this would be minus 0.930 molar. Okay. So what was the question? How many moles of CO2 are present at equilibrium? All right. So let's just focus on this one. 2.98 minus 0.93. 2.98 over 0.93 minus. So we have a 2.05 molar concentration of chloride, the chlorine. But the question was, how many moles? Well, it's this molarity in 2 liters. Remember the expression molarity is equal to moles per unit volume. So if we want to know moles, we say molarity times volume in liters. So molarity here times volume is equal to 4.10 moles of chlorine. All right, now why is that not the right answer? Well, I'm off by, how much of them? I'm off by a little. Did I make a miscalculation up here? Maybe. No, that should be right. Well, A is the closest. I just don't know why they're saying it's 3.99 and I say it's 4.1. All right, let me go back over my calculations. 2 into this is 1.07, that's correct. 2 into 5.85. Oh, that's it. 2.93. That's the problem. I was on the right track, I just made a miscalculation. 2.93 and 0.93 minus that is 2. Right? Yeah. Times 2 is 4. All right, so that's closer. I don't know where they got 3. It must be a rounding error. 3.99. I must have used more decimal places up here in preparing that question. Okay, but the procedure is correct. I was concerned about the procedure. Good. Yeah. 33. Okay. At minus 80 degrees Celsius, K for the reaction N2O4 yields 2NO2 is 4.6 times 10 minus 8. So we got this reaction again. We looked at this one before. N2O4. Yep. Gas is in equilibrium with 2NO2 gas. And at minus 80 degrees, C, the K equals 4.66 times 10 to the minus 8. Okay. We introduce 0.047 moles of N2O4 into 1 liter vessel and let equilibrium be established. All right, so initially, we have 0.047 moles in 1 liter. So this is molarity. And we got none of that. Okay. Let me see. The K for that reaction. All right. When they just say K, they don't say KP. They're talking about molarity. Right. So if we're going to find out total pressure, what we need to do is find out total moles of gas in that container. See where I'm headed? We're going to use the ideal gas equation, but we got to know the total number of moles, right? We got the temperature, we got the volume, 1 liter, we need moles, and then we can calculate pressure. So the change is you're going to lose some to get over there. And you're going to end up with 2x here. So 0.047 minus x, and then plus 2x. So our equilibrium is 4.66 times 10 to the minus 8 is equal to 2x squared over 0.047 minus x. Right? Now, with this small a value of k, this x is going to be insignificant. Because not very much is going that way. I mean, 10 to the minus 8, there's going to be a minuscule amount over here. So what we can say is this is infinitesimally smaller than that one. So what I'm going to do is say, let's see, is that going to help us? See, it would be 4x squared. Let me work this one out here. 4x squared over 0.047 minus x. Bring that one over here. Over there. Yeah, it's going to be a quadratic. Yeah. Let's say this is approximately equal to 4x squared over 0.47. 0.047. Okay, did everybody get that jump? Because it's such a small k, it's not going that far very much. We're not going to lose a whole lot of this. That means this is essentially the same value as it was before. Okay, now let's take this value times that value. .047. So this one times this one is on this side of the equation. And it's 2.19 times 10 to the minus 9 equals 4x squared. Now we're going to say x squared is equal to this number divided by 4, which is 5.476 times 10 to the minus 10, and then x is equal to the square root of that value, which is 2.34 times 10 to the minus 5 molar. Okay. So this is the value of x. And if we say this value of x in here subtracted from 0.047. So the concentration of N2O4 is going to be 0.047. Subtract that 0.46, 0.47. It's basically the same number. So the concentration of N2O4 is essentially 0.47 molar. Times 1 liter is how many moles? Right, it was 1 liter, wasn't it? Yeah, 1 liter. So molarity times volume equals moles. Times 1 liter equals 0.047 moles of this gas. How about this gas? Well, NO2 concentration is actually 2 times X. 2.34 times 10 to the minus 5 molar. Which is 4.68 times 10 to the minus 5. And times 1 liter is 4.68 times 10 to the minus 5 moles. All right, we did all that. And actually, we could have simplified everything. Because saying not much of this is going to be produced, that means we won't lose any of this. So basically, the number of moles of gas in there is still 0.047. Right? If we add this to that, to even 3 significant figures, it's going to be the same. So the moles of gas is 0.047 moles. Okay? So if we go to the gas equation and solve for moles, we get PV over RT. I might have to erase some of this. Oops, we want pressure. Sorry. Solve for pressure. Pressure equals nRT over V. Okay, so the number of moles is still 0.047 moles times 0.08206 times temperature, which is minus 80 plus 273. 193 Kelvin. Divided by volume, which is 1 liter. Okay, so the pressure is going to be 0.047 into 0.08206 times and 193 times. I get 0.74 atmospheres. B. Could have saved us a whole lot of time if I'd have just jumped straight from 0.047 to not much there. 0.047 is the final moles and plugged it in the equation. I don't know, maybe I would have lost somebody if I'd done it that quick. This illustrates the point that with a very, very, very low K value, you're not going to get much product. Whatever you started with is what you end up with. All right. Got next 34. Okay. Times reasonable. Okay. A sample of solid ammonium nitrate was placed in an evacuated container and then heated so that it decomposed explosively according to the following equation. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres at a temperature of 500 degrees K. Calculate Kp. All right, so here's our reaction. Ammonium nitrate, solid. And it decomposed to N2O plus 2 waters. Yes. Here we go. Let's see. Initial conditions. Let's see what they are. We don't know. They just put a certain amount in there. All we know is what we have at the end. At equilibrium, the total pressure in the container was 2.63 atmospheres. So the total pressure equals 2.63 atmospheres at 500 degrees. Let's say that Kp is going to be equal to N2, actually, it's this way. Pressure. That's a solid, so it's not going to be there. Pressure of N2O times the pressure of H2O. That's what Kp is. So 2.63 is equal to these values. Pn2O and pH2O. Oops, sorry. That's not right. All right. Squared, sorry. Squared because of that. So if the total pressure is due to the pressure of N2O, which we could say is X, and then the pressure of water, which would be twice that because of their ratio, correct? So 3x is equal to 2.63, and x equals 2.63 divided by 3. Which is 0.877. So this is 0.877, and this is 2 times it. 1.753. So now if we take N2O is 0.877 atmospheres, and 1.753 squared, and I'm going to square it, it's already in my calculator, and then 0.877 times, I get 2.70. Okay. So you're probably wondering, how did he do that? Well, we're given the total pressure. I needed to write the Kp so I understood what the equilibrium was all about. Pressure this, pressure that squared. So I knew that. I needed to find values here. I knew that stoichiometry said if X is produced from this for this one, from that decomposition, then you'd have twice as much for this one. And Dalton's law of partial pressure says this one plus that one has to equal that one. So that's where I set up. This one plus that one is 3x. That's where the 3x came from. Is this one plus that one. And set that equal to the total. And that's how I found my x. Okay. $36. All right, at a certain temperature, K for the reaction 2NO2 yields N2O4 is 7.5. If 2 moles of NO2 are placed in a 2-liter container and permitted to react to at this temperature, calculate the concentration of N2O4 at equilibrium. All right, so let's set this up and get an idea of what's happening. These are both gases. And the K is given to us as 7.5. I don't know why they put units in there, because we never do. 2 moles of NO2 are placed in here. 2 moles in what volume? In a 2-liter container. So 2 moles in 2 liters equals 1 molar. And then we have nothing here. That's the initial conditions. What's the concentration of N2O4 at equilibrium? Okay, so we're going to have a change, and then we're going to have an equilibrium situation. So we're going to, we know it's going that direction, so we're going to lose. Let's say we want to solve for X. We want to end up with something over here, X. And we're losing half of that. Correct? Right, because it's 2 to 1. If we get 1 whole over here, that means, oh, excuse me, my mistake. We lose twice as much. All right, so this is going to be X at equilibrium. This is going to be 1 minus 2X at equilibrium. And that 7.5 is too big to ignore the X value. Okay. We're going to lose a lot of X from here, substantial amount there. So we have to keep the X. We can't simplify it any further. All right. So our expression then would be 7.5 as K equals, equals N2O4 over NO2 squared. So that's X in the numerator. And in the denominator, we have 1 minus 2X squared. So that's X up here, and let's go ahead and expand this one. So that's 1 squared, and 2X squared is 4X squared. 4X squared, and then 2X minus 2X and minus 2X is minus 4X. So that's the expanded quadratic there. So let's bring that over here. 7.5 times 1, and 7.5 times a minus 4 is 30 minus 30X here. And then 4 times that would be plus 30X squared is equal to X. So far, so good. And then let's bring this X over here. So that's another minus X. 7, let's rearrange it. 30X squared, because that's A. And then this X becomes a minus, so we got a minus 31X. And then plus 7.5 equals 0. Now we can put it in the quadratic. So X equals minus B. A minus 31 plus or minus square root of B squared minus 31 squared minus 4 times A is 30 times C 7.5, all divided by 2A. There we go. So let's take this one and find out what that value is. Square this one, and minus, or enter 30 times, 7.5 times, minus, and then take the square root. So this value is 7.81, 7.81 from here. And this is a plus 31. So 31 plus or minus 7.81, all divided by 60, 2 times 30. So X is equal to 31, 7.81 plus, and then 60 divided is 0.647 or 31 minus 7.81 divided by 60 is 0.38. So which one makes sense? Well, 0.647 times 2 is greater than 1. Can't do that one because that'll make a negative. So it has to be 387. And go back to the question. What's the concentration of N2O4? All right, we just need to know X is 0.387. Molar. Oh, wait a minute. Yeah. Or round it off 0.39. Okay. I think that's it. Yep.